So we'll get started here. And so again, for those of you who have no idea what a vector is all about, we have two things called a scalar and a vector. Now, a scalar we're used to dealing with. A scalar is a quantity. And again, a quantity is anything you can count that's specifying magnitude only. Which means it only talks about its size. So for example, let's see here, we've got 5 apples. You go 80 kilometers an hour, for those of you who can drive. Somebody might weigh 200 pounds. Those are all things you can count. You have 10 liters of gas. So it just specifies magnitude only. And again, magnitude means a number. So all of these quantities are just represented by a number. Now, when we get to talking about a vector, that is when a quantity specifying magnitude and direction. So for example, we could have, like I used that wind up there, or that 80 kilometers an hour. Well, you could say the wind is 80 kilometers an hour, but you could also say it's from the east. Or for me anyways, Toronto is 120 kilometers west of me. Or for those, again, in my physics class, we could say the acceleration due to gravity is 9.8 meters per second squared. And of course, the direction of gravity is down. All right, so again, the key here is a scalar, which we're used to dealing with in life all the time. You're just counting whatever you can count. But a vector has two aspects to it: magnitude and direction. So a number plus the direction. All right, now drawing a vector. All right, so draw a vector that begins at the origin and finishes at 0.68. So again, just a little bit of a sketch here. Let's see, I'll say we're going out to 6 here, and let's see, up to 8. And so our vector starts at our origin, where the tail would be, and ends at 6, 8. And your start at the origin, and then our tip, our arrow point, is at the end of that vector. And I could call that, again, vector V, I guess. So a little vector symbol with an arrow on top of it. And so I could say that point P here is equal to vector OP, which from the origin to the end of P, which in this case is vector V. Now the other thing is that when I have the absolute value bars, which don't get talked about much in math class anymore, this is what we call the magnitude of vector OP. So that's the magnitude, or size, I should say, of vector OP. I'm going to put a vector symbol above that OP. So that's a little notation. Now if I'm finding the magnitude of vector V, in this case I can use the Pythagorean theorem, where I know the legs of the right-angled triangle. And so to find the magnitude or the size of vector V, I can use, like I said, the Pythagorean theorem, where the V squared is equal to, in this case, 6 squared is one side of that triangle. And this side here, of course, would be 8. So we'd have plus 8 squared. And so the magnitude, or the size or length of our vector, so that's a size. I should also put in length of our vector. Again, is going to be, let's see, V squared is equal to 6 squared is 36. 8 squared is 64. Add those two together, I get, let's see here, 100. Then, of course, I would take the square root of both sides, and so in this case, the length, or the sides of vector v, is 10. All right, so if you're talking about the vector, it's vector v, but if you're just talking about the length of it, then you have the absolute value bars around that vector v. All right, now that's talking about the size of the vector. Again, there's two things with the vectors. There's the size and the direction. And so next up here, given vector v, the magnitude, I should say, of vector v is 25 in this case. Find vector v. And so I'm just, for example, I'm going to draw a vector out here, just like I did before. I'll put a 50-degree angle right here. And now when you're talking about the bearings or direction, you have what's called a compass rose. So we don't have an XY axis here. We have northeast, southwest. And to draw them on there properly, what I use is, and a good rule to follow in life is never enter stinky washrooms. And so in this case, if I was to write down what vector v would be, first of all, I know it has a magnitude of 25 meters per second. Now, again, with a vector, you need the direction. And so in this case, we start at north and we move 50 degrees towards east. And there is vector v. All right, so again, it has magnitude and direction. The other thing, let's try another one here. I'm going to draw another vector v. So again, I should put that in there. That's vector v. This one's going to be vector v2. I'm going to say that there is a 20-degree angle here. And so again, when I'm writing down or defining vector v, writing it down as magnitude and direction, again, the magnitude here is not changing. It's 25 meters per second. But in terms of the direction, I could say it's, I better put my compass rose here, never enter stinky washrooms. And in this case, I could go west. Oops, that's a terrible W. I start at the west, and I move 20 degrees towards the south. Now, vectors, there's actually two ways you could define them, because again, we have a right angle here between west and south, and so it's a 90-degree angle, which means it's 70 degrees right in here. And so really, I could also write down vector v as 25 meters per second. But I could also say, well, you could start at south and then move 70 degrees towards the west. There we go. So every vector can be represented two ways. The magnitude is not going to change, but your direction, again, you can change your perspective. All right. Now, what else we got here? Opposite and equal vectors. So again, this is a little bit different view than I've had in a science class, such as physics. But we have square here, A, B, C, D. All right. And so when we're talking about opposite and equal vectors, I could say the vector AB, so we'll call that vector AB there in blue, I could say it's equal to CD. Just like I could also say, for example, BD, which starts at B down to D, is equal to AC. Whoops. A to C, not C to A. We'll get to that. So A to C. And the reason I could say that these are equal vectors, or equal or equivalent vectors, equivalent. Oh, I always struggle with that word. Equivalent. All right, I was going to leave it. Equivalent vectors is that these vectors are equal in magnitude, so they're the same length, and same direction. Now, opposite vectors, when I'm looking at those or thinking about those, is if I look at, say, if I compare, so we'll go but if, I'm say vector x here is equal to, say, CA, which again, let's see here, I'm going to erase my blue and green lines here. So if we have CA is equal to vector x, then BD, which goes the opposite way, but again, equal in magnitude, equal in length, I could say that was what we say negative vector x. It's the opposite. So they're equal in magnitude. I'd say that there are opposite. So CA and BD are what we call, BD, are opposite vectors, as they are equal in magnitude, again length, but opposite in direction. And that makes them opposite vectors. So you got to have the same magnitude, and but opposite direction, you have opposite vectors. You have equal vectors where both things are equal. Now, a rarity, but it does happen, is the zero vector, the old zero vector, which I write with a big zero and a vector symbol over it. And so again, this is our zero vector. And again, when we talk about the tail and the tip of a vector, the tail is the starting point, the tip or the arrow part is your tip. And in that case, the tip and the tail are at the same point because you've gone nowhere. Your start and your end are the same. So an example of that, because we're going to get to adding vectors, is if I take, say, let's see, a vector u, and then when I'm adding vectors, I draw them tip to tail, and then I get, so vector v moves this way, and then let's see, I'm going to have a third vector, which I'll call, I guess, w. And so in this case, if I take u plus v, add these vectors up, plus u, or w, sorry, well, your starting point and your end point are the same, and so we would get the zero vector when we add those vectors up. All right, now expressing those vectors. Again, this is a little bit of a different perspective. We look at vectors in 2D and 3D. So I'll start off with 2D here. We got, it says find vector AB. Well, if AB is a vector like at the top there, well, a vector similar to that would be, or not similar, equal in magnitude, opposite in direction would be vector CD. And if I had, let's see here. Well, actually, I don't want CD. Let's go with BD. I just did CD. So if I had vector BD, where's that from? Down towards that. Well, a vector equal in magnitude, same direction, would be AC. Now the last one here, it says, what's the same as the magnitude of BA? What vectors have the same size as BA? Let's see here. Whoops, draw a line in red. Well, I'll tell you what, AB would be, because it's an opposite vector, equal in magnitude, but opposite direction. Also, CD would be a vector that would have the same size. And, well, also DC would also have the same size. So again, all I'm worried about in this situation, because of the absolute value bars, is the magnitude. All right, now I've got a 3D situation here in B. All right, and so it says find a vector that's like A to B. And in this triangle, it's shifted way down, but DE would work. Again, equal in magnitude, same direction. CB, where's CB here? From right across. Well, again, a vector that's equal in magnitude, same direction would be F to E. It's another one here. BE, where would BE look same direction? Well, B to E, you could have A to D, same magnitude, same direction. And in this case, actually, you could also have C to F. Whoops, that's a terrible line, but get the point here. C to F would be the same. So there's a couple vectors that are equal in magnitude and same direction. Then let's see, what else we got here? Oh, now we're into magnitude again. Let's clean this diagram up here. What has the same magnitude as BC? So it's just the same size. Well, I would go EF could. Whoops. It's terrible there. It would have the same size, and guess what? So would FE. Oh, put a vector symbol in there. And you know what? So would CB. Those vectors would have the same size. What else we got here? DF. D to F. So what else has the same size as D to F? Well, FD would, for sure. And so would A to C and C to A. Again, only worried about the size this time out. Now, for all these examples, the key thing here is to know is that your position in space is not important. It doesn't matter where you are. It's just the magnitude and direction that are important with vectors.